Hi, and welcome to this geometry gem where I'm going to expand on my previous geometry gem where we learned how to find the local coordinates of a point in a local coordinate system, not the world coordinate system. And now what we're going to do in this geometry gem is to figure out how to now recreate that local point from a reference system into into a new local coordinate system. This operation is typically referred to as change of basis. So what you have here, for example, is you can see that I have this point in reference to this plane, and you can see that this point, now that I have created with this algorithm, is basically maintaining the same x, y, z local relationship with this plane than the original one had with this other plane. Think of planes as coordinate systems, is the same. And the idea is that this operation is really good because it allows us to do basically reorientation of geometry from one local coordinate system to another local coordinate system. Like for example, I have in this exercise where I have created a surface, and in this surface I have found a lot of tangent planes, and what I have done here is that I can use my algorithm to replicate the relationship of this point to this target plane, to this source plane, with any of those planes here. So I can now create like a collection of points with that same orientation here on top of this surface. Similarly, what I can do is I can, for example, apply this application. I can apply this to any geometry. So, for example, if I have a mesh that has a bunch of vertices and faces connecting them, basically I can extract all those vertices because a mesh is just a collection of points that are connected with faces. And if I translate and reorient each one of those vertices, then I can end up with a cylinder that has the same relation to that coordinate system than the previous one. So effectively, having reoriented this geometry from one local coordinate system to another coordinate system. This exercise is building on top of my previous gem. So if you haven't checked that out, you probably want to give it a look before we go into getting hands-on. And before we go into getting hands-on, let me please explain how we're going to be doing this by explaining it conceptually with a couple of diagrams. Let's take a look at that. So let's discuss the problem. As we said, we're going to be building upon what we've learned in the previous gem, where what we were able to do was to find for a point that was defined in world coordinates, what we were able to do was to find what the local coordinates of this point for a particular reference system like this one could be, right? And this is going to be the basis of what we want to do in this gem, because in this gem, what we want to do is we want to say, well, we have a point defined in some kind of local coordinate system, all right? And then we have now some other coordinate system that is somewhere else. And what we want is we want to create a new point in that coordinate system that has the same relation from the old point to the old coordinate system. So whatever the local coordinate system, the local coordinates of that point in the first system are, I want those local coordinates to be the same for the new point that I'm going to be creating in that new reference system. And ultimately, because I always need to work in world coordinates, I will need to be able to find what are the world coordinates of that second point. The idea is the following. Imagine I have this point and I have been able to find, I know it's x, y, z in world coordinates. I know what the local coordinates of this point are. And then I have some other coordinate system that is somewhere else in the world. What I would want to do is I would want to be able to take the x, y, z local coordinates and I apply them in this system so that I would end up with a point that maintains the same relation with this coordinate system than this point maintains with this coordinate system. And then what we're going to do is going to be very simple. What we're going to do is we're going to take the origin of this point, the origin of this coordinate system, and then we're going to add to that origin, we're going to add a position vector that is going to be pointing this way, and it's going to be the result of the x-axis multiplied by the x coordinate times the y-axis multiplied by the y coordinate and the z-axis multiplied by how many units in the z-axis this point should be. Let me actually draw a diagram where we see that more clearly. So let's zoom in the new coordinate system that we have, and let's zoom into the problem of we know the XYZ local coordinates of the point that we want to generate in this coordinate system. Okay, because now we need to figure out how to do that. With vector algebra, it turns out that it's also very easy to do with vector transformation, because, for example, if we know that the point that we want to get is in x units along the x-axis, y units along the y-axis, and z units along the z-axis, so those three numbers that we have there, what we can do is we can just multiply each one of the three axes, so we can scale it x, y, and z. We can scale the three axes of the reference frame. And then with those three vectors, if we add them together, what we obtain is a position vector that looks like this. What we obtain is a position vector that looks like this. It's a vector that contains, that is the addition of the three vectors. It's a vector that has the three coordinates x, y, z of those Cartesian systems. And then after that is very easy to do. In order to find the coordinates of point P, the only thing that we need to do is take the coordinates of the point O, the origin of this reference system, and just add the vector that we have found in three-dimensional space with this coordinate system. So it's a very simple rule. P, the point that we want to find, is going to be equal to the origin moved by that position vector. So let's get busy. Should we see how to make that with code? All right, so let's get started. We're going to be implementing this in C# for Grasshopper, which is a procedural modeling environment that is a plugin for Rhino. But this process that we're going to follow applies to any framework that you can think of that has some kind of geometry kernel. Grasshopper happens to have plane objects, and plane objects being this structure that contains three orthonormal unit vectors, x, y, z, representing the orientation, and a point that represents the origin of that plane. We can think of this, if you're more into 4x4 matrices, you can think of that as the three vectors as the rotational part of the 4x4 matrix, and the origin as the translation part of the rotation matrix. It's basically the same concept. And I'm going to be building upon the work that I have done in my previous gem, where we discussed how to, given a point and given a reference system, how to find the local XYZ coordinates of that point for that coordinate system or for that plane. So what I'm going to do is, what I have done is I have created a second plane, also from 3 points using functionality that is available in Grasshopper. And then what I'm going to do is I'm going to extend this exercise so that I can now generate a new point that is going to be at the same local coordinates at this point as this point in this plane for the new coordinate system. And I would like to find what the world coordinates of that point are in this new reference frame. So what I'm going to do for that here is I'm going to rename first. I'm going to rename the plane. So I'm going to call it source P, and then I'm going to create a new input in the component that is going to be target plane or source. I'm going to call this source coordinate system, and I'm going to call this target coordinate system. I kind of like that definition a little better. I'm going to plug this in here, and I'm going to remember that I need to right click and set that the type of this input is of the type plane, which is how in Grasshopper coordinate systems, frames, or 4x4 matrices are defined. Okay. Now I'm going to delete the outputs, and what I want for output is what I want to do is the new point, the point that is going to be, or the point in new C coordinate system, for example. Or no, I actually don't like reoriented point. I'm really bad. This happens to me all the time. I'm really bad with like coming up with names for things. Okay, and then as I double click, you can see that the code that we have is from the previous gem, where we created a function called local coordinates that we use to find from a point in world coordinates and a coordinate system, find a point with the coordinates in that local coordinate system. What I would like to do now is I would like to create another function that is given a point in world coordinates, given a point in local coordinates, find what that point in world coordinates would be for a particular plane. So the process that I have described before. So what I'm going to do is I'm going to create a function called point on plane. All right, for example, and I'm going to say that is going to have the x coordinate, the y coordinate, and the z coordinate. And I'm going to say something like this. Okay. So I'm going to create a function that, given a plane and given x, y, z coordinates, it generates a point that is on the x, y's. And I'm going to call it local point on plane. All right. And this, the return type of this should be a point 3D object, because what I want is that object. Okay. So this is going to be very easy now. As I described before in my drawing, what I will need to do is I need to create a vector 3D object that is going to be called the position vector, which is going to be equal to the x direction of the plane scaled by x. So that's going to be x times cs dot x-axis, so the x-axis vector of the plane that I have multiplied scale by those x coordinates, plus y times cs dot y-axis plus z times cx dot z-axis. All right. So remember, according to my diagram, what I have just done is I have created a vector that is a combination of the x-axis scaled by x plus the y-axis scaled by y plus the z-axis scaled by z. I have my position vector now. So what I can do now is, in order to find that point, so in order to find the point 3D pt or p, whatever I want, what I can do is I can say I want that point P to be the origin of the plane plus this position vector that I have defined. So that is going to be very easy again. In Rhino, I can use the multiplication operator I can use the addition operator to add points and vectors. So in Rhino, what I can do is I can say this is going to be equal to cs dot the origin, so the origin of the plane, plus that position vector. All right. If you don't have that possibility on your framework and the framework that you're working with, an alternative could be to just say point 3D P is going to be equal to a new point object, all right, which has cs dot origin plus the x coordinate of origin dot x plus the position x, then the second coordinate of this point is going to be the y coordinate of the origin plus the y coordinate of the position vector, and then cs dot origin, the c location of the origin plus the c coordinate of the position vector. All right, these two operations are actually the exact same thing. So I'm going to, this will be manually, and this is going to be using Rhino common operators. Okay, so they're both equivalent. And now my function should just return that point P. Okay. So what I could do now is very simply, I can just say, well, I have point P is the local coordinate of the point that I have been given in the source coordinate system. All right. And now what I can do is I can say point 3D new P is going to be equal to a local point on plane with P dot with on target coordinate system, and then p dot x, p dot y, p dot z. And then the output of this reoriented point should be equal to that new p that I just created. Let's see if this works. Oh, is this working? Let me see. So it looks like this point is like on the x and y is like a little over x and y, and here it is on the other direction, because here you see that the two directions are flipped. Okay, so this is x and y. Let's do an exercise. Let's see if we use vanilla Grasshopper to find the coordinates of this point in this coordinate system. We should get something like something like this. Okay, but if we do it on the other one, we should get the exact same thing, which we are not getting. Oh, sorry, the other point. Oh no, because yeah, because it's sorry, this is not the check really. So this should be the reoriented one. Exactly, the reoriented one should have the same coordinates as this one. All right, exactly, yes. Okay, this is what happens when you rush things. You see, because this point, the original point, should have the coordinates on this plane, these ones, and this new point that I just created, this one here, should have the same local coordinates on this plane. So that's what was happening here. All right. Now, why are we doing this? Why is this useful? Well, this has been very useful because now, if I move this point, you can see that whatever transformation I do on this point, this other point is going to keep the same relative location to that original point. But let me actually do a quick exercise on like why this could be cool. Let me show you an example of a cool application of this. Hold on there. So check this out. Really quick exercise. I have created a loft surface in three-dimensional space. It's an Earth surface, so it has UV directions in both its main directions. I have brought that into Grasshopper, and then what I have done is I have divided this surface into a grid of UV tangent planes. So each one of the planes is tangent to the surface, okay, and it's maintaining its relative orientation. So now what I've done is I have plugged, instead of using the original target plane that I used in the exercise, what I have done is I have plugged each one of all these planes into the target translation. So basically what I'm doing now is that for each one of these planes, I am creating a new point that has the same local coordinates. Then these two relationships, it has them here in the so each one of these points is holding a relation to its reference plane, the same one as we can see here between this point and the source target plane. So why is this interesting? Well, it's interesting because like it can give us a way of like offsetting the surface or making operations with the surface or with elements of the surface. Or if, for example, if I had a mesh object, let me actually do that with a mesh object. Hold on. So with a mesh, it looks something like this. I have created a simple cylinder mesh in Rhino. I have brought it into Grasshopper, and I have deconstructed the mesh into vertices, faces, colors, etc. Everything that is contained in a mesh. But at the end of the day, think about meshes as just point clouds that are joined with triangles. And because each one of the points, each one of the vertices of a mesh is a point, what I can do is I can feed all the points of the mesh to this tool that I have created to take the points from this coordinate system into a different coordinate system. And the result is that what I get is basically that cylinder translated from this coordinate system to this other coordinate system. So if I move it around, you can see that the relative position between the two elements is maintained the same. You can see that the cylinder is now kind of intersecting the plane, right? And you see how the cylinder is also like holding the plane here in three-dimensional space. And finally, because in Grasshopper I have the connectivity of the faces. I can reconstruct that mesh in 3D space by using the translated vertices, but using the same connectivity of the faces. All right, so therefore I have now my translated cylinder from one local coordinate system to the other local coordinate system. Okay, I think this is pretty cool and pretty neat. This operation can also be done, change of basis can also be done with matrices. It can also be done with special transformations in 4x4 matrices. But I wanted to break down first like the fundamentals of this process, and maybe at some point in a future geometry gem we can take a look at how change of basis actually looks from a more with a matrix operation. Okay. I think this is what I want to stop here. Thank you very much for sticking around. I hope this was fun and useful for you. I think I might be using this technique of finding XYZ locations of a point in a local reference system very often in my future geometry gems, like for example the one that I'm thinking of recording next, which is going to be just stay tuned and you will see what that happens, what the geometry gem is. Thanks a lot for being here. If you like what you saw, please subscribe, hit the like button, notifications, all the good stuff. Show your love, spread the word, tell your friends, and all those things. Okay. And in the meantime, I'll see you on the next video. Thanks a lot.